Hey everyone and welcome. Today we're diving into a Leetcode problem called sort colors. It sounds simple, but it has a really neat and efficient solution. We'll break it down step by step, so don't worry if it seems tricky at first. Let's get started. So what's the challenge? We're given a list of items. Let's call this list. Each item in this list is colored red, white, or blue. But instead of actual colors, we're using numbers: 0 for red, 1 for white, and 2 for blue. Our job is to sort this list. That means we have to rearrange the original list itself, without making a brand new one. The final list should have all the reds, that's the zeros, first. Then all the whites, the ones. And finally, all the blues, the twos. Oh, and we can't use the built-in sort function from the programming language. There's also a follow-up asking if we can do this in just one pass through the list, using only a tiny constant amount of extra memory. Let's look at an example to make this clearer. Suppose our input list is 2, 0, 2, 1, 1, 0. After sorting, it should become 0, 0, 1, 1, 2, 2. See how all the zeros are at the start, then the ones, then the twos? Another quick one. If is 2, 0, 1, the output should be 0, 1, 2. Simple enough, right? The trick is how we get there efficiently. Okay, so what's a straightforward way to tackle this? Well, we could first go through the list and count how many zeros, ones, and twos there are. For example, if we find 2 zeros, 2 ones, and 2 twos, then in a second pass, we could just fill the original list, put in 2 zeros, then 2 ones, then 2 twos. This works, and it sorts in place using very little extra memory, just for the counts, but it takes 2 full passes over the array. The problem hints at a one-pass solution, so let's see if we can find one. So how can we do this in a single pass? There's a classic algorithm for this, sometimes called the Dutch national flag algorithm, because it's like sorting the 3 colors of the flag. The core idea is to use 3 pointers, or markers, let's call them maanwoord. The pointer keeps track of the boundary for our zeros or reds. Everything to the left of will be a 0. The pointer is for the current element we're looking at and deciding what to do with. And the pointer keeps track of the boundary for our twos or blues. Everything to the right of will be a 2. Elements between and de Crowley will be ones, or whites, that we've already processed. Think of our list as being divided into sections by these pointers. The section from the beginning up to just before will hold all our zeros. The section from up to just before will hold all our ones. The section from up to is the part we're still working on, the unknown region. And the section from just after to the end of the list will hold all our twos. Our goal is to shrink that unknown to region. We'll do this by looking at the element at the pointer. So initially, and start at the very beginning of the list, index 0, and starts at the very end of the list. We keep going as long as hasn't passed. Inside our loop, we look at the number at the position. If this number is a 0, perfect. Zeros belong at the beginning. So we swap the number at with the number at. Then we move both and one step forward. If the number at is a 1, that's also good. Ones are supposed to be in this middle section. So we don't need to swap anything. We just move one step forward. Now, if the number at is a 2, twos belong at the end. So we swap the number at with the number at. Then, we move one step backward. But importantly, we don't move yet. Why? Because the number we just swapped into the spot it came from the end could be anything, a 0, a 1, or even another 2. We need to recheck this new number in the next iteration. Alright, here's what that logic looks like in Python code. I know, code can sometimes look a bit dense, but no worries. We'll walk through the key parts nice and slow, explaining what each bit does in plain English. This is the entire function that sorts the list called. First up, we set up our 3 pointers. The pointer starts at index 0, which is the very beginning of our list. The pointer also starts at index 0. And the pointer starts at the last index of the list. We can get this last index by taking the total length of the list and subtracting 1. Next, we have our main loop. This loop will continue to run as long as our pointer is less than or equal to our pointer. Once passes, it means we've processed all the elements, and the list should be sorted. Inside the loop, we first check the element at the current position in our list. If this element is a 0, we know zeros belong at the front, so we perform a swap. The element at and the element at trade places. After the swap, the element now at is a 0, and in its correct partition. so we increment to expand the buffer. We also increment to move on to the next element to classify. What if the element at is not a 0? We then check if it's a 1. If it is a 1, well, 1s are kind of in the right place, at least for now. They belong between the 0s and the 2s. So, we don't need to swap anything. We simply increment our pointer to move to the next element. Finally, if the element at the pointer is not a 0 and not a 1, it must be a 2. 2s belong at the very end of the list. So, we swap the element at pointer is not a 0 and not a 0 and not a 0, plus people swap the element now at pointer is not a 0 and not a 0, is a 2, correctly placed in the pointer is not a 0, so we decrement to shrink the unknown region from the right. Crucially, we don't increment here. The element that just got swapped into the position, it came from the position, needs to be processed in the next iteration of the loop. It could be a 0 or a 1, so we need to re-evaluate it. So how efficient is this Dutch national flag approach? It's pretty great. For time complexity, it's big O of n, or order n. This means the time it takes to run is directly proportional to the number of elements in our list. Each element is visited and processed by the pointer, essentially once. While elements might be swapped, each swap moves an element closer to its final sorted partition. For space complexity, it's big O of 1, or order 1, which means constant space. We're only using a few variables for our pointers regardless of how big the input list is. We're modifying the list just like the problem asked. This is very memory efficient. So, to recap, we tackled the sort colors problem, which asked us to sort a list of 0s, 1s, and 2s. While a simple counting sort works and is 2-pass, the Dutch national flag algorithm provides an elegant 1-pass solution. It uses 3 pointers and to cleverly partition the array in place, achieving an order n time complexity and order 1 space complexity. It's a fantastic technique for these kinds of partitioning problems. Hope that breakdown made sense and helped you understand the sort colors problem and its clever solution. If it did, feel free to hit that like button, subscribe for more Leetcode explanations, or drop a comment if you have any questions or other ways to solve it. And hey, if you're feeling super generous, you know, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll catch you in the next one.